Hi, everyone. Thanks for joining us today. I see some folks are starting to trickle in. We can give it a couple minutes. And really excited to have you all with us for our second NASA Break the Ice Challenge webinar. We are in store for a really exciting event. I would like to preface by saying, unfortunately, Don Thomas, the former NASA astronaut, who had agreed to join us, is now unable to, but we hope to have him for a future event. And I know that he is disappointed he couldn't make it, but we're still really thrilled to have you here, and we still have a group of really good panelists that have a lot of good information to share. As a reminder, this webinar is being recorded, similar to the last one. And like the first webinar, this one will also be published both to the challenge website and our YouTube page. And we will be emailing that out. If you're on our any of our email lists, you'll be receiving that in your inbox in the next few days. We will be answering questions as mentioned. I know we received a couple even before the webinar, and I see one's already trickled in. So we'll save those for the end, and we'll make sure that the right individual out of our panel is answering the right questions. So please, ask as many questions as you'd like. The goal here is to be as thorough and leave no stone unturned. And I think without further ado, we can go ahead and get started. Naveen.
Thanks, Adam. Hello, everyone. Welcome to NASA's Break the Ice Lunar Challenge webinar, and thanks for joining. This webinar is being recorded. Before we move on, I would like everyone to know it is with our deepest regrets that former astronaut Don Thomas had to cancel his attendance with us today due to unforeseen circumstances. Astronauts are pretty good at controlling things like, rockets, spaceships, and other life-threatening situations. But one thing they can't control is their schedule. NASA came up with a solution for this, and it involves changing the length of the day from 24 hours to about 708.7 hours. And the only way to achieve this solution is to send astronauts to the moon for a permanent presence, and we need your help with that. We hope to have Don available for you in future webinars. I'm Naveen Vecha, Challenge Manager for Break the Ice Lunar Challenge. I support NASA's Centennial Challenges program through Jacob's Space Exploration Group. Today, we are going to share some basic information about this challenge and hear from a panel of experts on technologies that have applications ranging from the deep oceans to the deep space. We hope you will compete in this challenge and help achieve NASA's goal of sustainable space exploration. Next chart, please. Go back. Here is today's agenda. I will introduce our team and we will go over some housekeeping items. We will provide an overview of the Centennial Challenges program and the Break the Ice Lunar Challenge. We will then hear from our panelists. Following that, we will take you on a tour of the challenge website. We will then take some questions from you and wrap up by providing some next steps to participate in the challenge. Next chart. Here is our team. Monsi Roman is the program manager for the NASA Centennial Challenges program. She has been leading this program since 2015. Before that, she worked as the chief microbiologist for the International Space Station's Environmental Control and Life Support System. You already heard about me. I'm Naveen Vecha, challenge manager for this challenge. And Adam Carrado is the chief of staff at Ensemble. Ensemble has expertise in supporting open innovation, digital transformation, marketing, and commercialization. Centennial Challenges program chose Ensemble to help with the promotion and administration of this challenge. On the right here are our panelists, Dr. Pete Carrado from BTIL Corporation, Dr. Chris Jackney from Honeybee Robotics, and Mr. Judson Kaufman from TerraDepth. With that, I'm going to pass it over to Adam.
Thanks, Naveen. As you can see, we have a really exciting agenda and are joined by a very esteemed group of panelists. For the logistics for today's webinar, I already touched on some of this, but we do really encourage your questions. We have received incredible questions throughout this challenge. We've done our best to answer them as quickly as possible. I know that might not be as fast as some would like, but it's can be difficult sometimes with needing legal review and whatnot. And but like I said, we do try to address all questions and believe we have done so. If we can't answer them during this webinar, we'll be sure to get back to you either via email or posting them on the challenge website as an FAQ. And as I mentioned, we will be recorded. This webinar is being recorded, and it will be shared on the challenge website and our YouTube page. And with that, I would like to pass it on to Mansi.
Good morning, everybody. Thank you to Naveen and to Adam for the introductions and all the information that needs to happen up front. I am excited to share with you today a little bit about what we are and how we came to be very quickly, because I am looking forward, as all of you are, to information that our panelists are going to give us related to some Earth applications of the technologies that we are looking for. So next chart, please. So the NASA Centennial Challenge was the first NASA prize program, and the first competition happened in 2005. The competitions are all very strongly aligned with NASA technology gaps and defined as defined with the agency roadmap and taxonomy area. So any competition that we run has a need within the NASA mission, and this one is not different from that. The competition development is supported by subject matter experts from NASA, academia, and industry, and today's webinar is an example of the subject matter experts that have helped us outside of NASA. And within NASA, the leads of these roadmaps had been involved in the development of each of the competitions. Therefore, when we finish, the results of the competition is some kind of technology that could eventually help NASA's mission. The program is guided by the NASA Prize Authority. It's a law. So some of you might be questioning how come we are asking you to have insurance and some other things that normally other competitions do not require. Well, that is all spelled out in the NASA Prize Authority, and you can Google it, and there's a link in here too, and you can understand some of the requirements we have to impose on you. And so if you want more information, happy to provide you that. Next chart, please. So NASA Centennial is part of the NASA Prize challenges and crowdsourcing program at NASA headquarters. We are part of the toolkit of the agency to provide solutions that come from the public, trying to help the NASA mission, as I explained before. But we definitely are not the only one. There's other tools in that toolkit that can be used, and they all can be found at the NASA Solve website if you want to go and get more information about that. Next chart, please. We are currently running 7 competitions, and I put in here the 3D printed hat challenge, even though that one has been completed and closed, because a lot of the information that was gained throughout that competition is tainting or giving some of the flavor of this new competition in Break the Ice. But in addition, if you're interested, we have a competition related to CubeSats. We have one related to vascular tissue, CO2 conversion from CO2 to glucose to feed bioreactors. We have one in space robotics related to robotic systems that can do ISRU missions on the surface of the moon and perhaps Mars. What's on the Moon, which is currently open for people to come and participate, is related to the power grid on the surface of the moon, and we are looking for help in the storage, distribution, and management of power. So if you're interested and have some information that you can provide to that other competition, please feel free to come in and look into that one. Break the Ice, which you're going to hear a lot about today, and we are very grateful for your interest. And Deep Space Food, which is related to the need to help feed our astronauts in long-term deep space missions. And we think, like any of our competitions, all of them have Earth applications, and of course that one does too. Next chart, please. So when we say we want you, we're not kidding. We're looking for people like you to come and join the NASA family in these competitions. We do really want to hear the kind of information that you might want to provide us. NASA is very good. We have lots of amazing experts in technology, but sometimes there is a little bit of a technology nudge that you might have that can help make things a little bit easier. So truthfully, we mean it when we say we want you. Again, I want to thank our panelists and Ensemble for putting this webinar together, and the leadership of Naveen, and have fun. This is going to be a good webinar. Looking forward to hearing all your questions, and thank you so very much to you, everybody that is listening today. So there you go, Adam. Thanks.
Naveen?
Yeah. Thanks, Monsi. I will now provide a short overview of the challenge. Next slide. The goal of the phase 1 of the challenge is to enable the development of innovative approaches to excavate lunar ice regolith and transport the acquired resources such as water under the extreme environmental conditions that exist on the moon's polar regions. We are particularly interested in solutions that maximize water delivery while minimizing the energy usage and the launch mass. Phase 1 provides a hypothetical mission scenario. Competing teams are asked to design a credible and feasible system architecture that addresses certain technology gaps. The system architecture should also meet certain performance requirements. The challenge timeline is shown at the bottom. Registration for phase 1 opened on November 18th. We conducted an informational webinar in December. The recording of that webinar is available on the challenge website. Here is today's webinar shown on the timeline. Deadline to register and submit solutions is June 18th. We are planning to announce phase 1 winners by mid-August. Next chart. Here is the prize purse distribution. Total prize purse for the challenge is $5 million. Prize purse for phase 1 is $500,000. Phase 2, if opens, will have a prize purse of up to $4.5 million and will last for 27 months. Our goal is not to exceed 3 years with this challenge. Prize breakdown for phase 1 is shown here with $125,000 for the first place, $75,000 for the second place, $50,000 for the third place, and up to 10 runners up with $25,000 for each runner. Teams may receive a maximum of 300 points. The point distribution is provided in the rules document that is available on the challenge website. In order to be eligible to receive a prize, a team must meet or exceed a minimum score of 100 points. Next chart. This challenge is a collaborative effort between multiple organizations. Centennial Challenges program, as Monsi spoke about it, leads the challenge design, formulation, and execution, and is also responsible for providing the prize funds. NASA Marshall Space Flight Center and Kennedy Space Center are the lead centers for this challenge. Subject matter experts from both these centers are heavily involved in the development and execution of this challenge. There is also some support provided by subject matter experts from NASA Langley Research Center. As mentioned earlier, Centennial Challenges program chose Ensemble to help with the promotion and administration of this challenge. Next slide. Before we hear from the panelists, we would like to show you the challenge promo. Our communications team did a fantastic job creating this promo. I hope you like it and will help us complete the story. Adam?
Our moon, the next step in human exploration beyond our Earth.
Can't see the video.
Our moon, the next step in human exploration beyond our Earth. In order to live there sustainably, we'll need habitats, water, fuel, and so much more. But we can't bring everything with us when we go. We need a way to collect valuable resources already available on the moon. The moon's regolith, or soil, can be used to construct habitats. Water hidden under the surface can be harvested for human use and for future propellant needs. But responsibly gathering these resources far away from our home planet will require technologies that aren't currently available. And with frigid temperatures, low gravity, and challenging shipping conditions, traditional Earth-based excavation technologies aren't going to cut it. That's where you come in. NASA's Break the Ice Lunar Challenge is looking to industry, students, small businesses, and garage inventors to develop innovative ways to excavate the moon's icy regolith and deliver water in extreme lunar conditions. These technologies and resources will be critical as we learn to live off-world, and your ideas could help us get there, extending sustainable human exploration to the moon, Mars, and beyond.
Thanks, Adam. To the presentation. There you go. All right, I hope you enjoyed watching this promo. It's available on the challenge website if you would like to watch it again or share with your colleagues. Now, it is my pleasure to introduce our first panelist, Dr. Pete Carrado. Pete is a consulting engineer and a lifetime fellow emeritus at Bechtel. He worked as a senior technical specialist at Bechtel Corporation for nearly 4 decades. He's a subject matter expert in civil and structural engineering and has supported major projects in different industry sectors, including solar, nuclear, mining, and metals. Pete helped with the design and formulation of the Break the Ice Lunar Challenge. Thanks, Pete.
Thank you, Naveen. Maybe just a little introduction to Bechtel for those who don't know us. We're probably the opposite of what you'd call a startup company. We've been around for over 120 years. We're a family-owned engineering, design, and construction company that started out with 2 mules and a wooden scraper by Mr. Warren Bechtel out in California. And in my more than 4 decades, I've worked for 4 Mr. Bechtels. So we're kind of unique in that there's still a Mr. Bechtel running the company. We got engaged heavily with NASA on Centennial challenges in 2016 when we started working on the Mars Habitat Challenge. Over our 120-year lifetime, We've done more than 25,000 major projects in 160 countries on all 7 continents. So we work all over the world and deliver a lot of unique projects, many of which resonate with this challenge. I'd like to show you a few. Can we go to the next slide, please? So we've been involved in space activities. That's Launch Complex 40 on the left. That was a Bechtel designed and constructed job. Down at the Kennedy Space Center, we're currently on the upper right is a picture of Mobile Launcher 1. We're currently in the process of designing and building Mobile Launcher 2, which will be used to support the Artemis missions. Actually, I'm personally involved in the one on the right, doing design reviews of heavy structural steel connections. On the bottom right is NASA Stennis, which is a big facility down in the Louisiana area, where a lot of testing and production of rocket motors took place. What you see on the right, this is where the Saturn V booster was tested. And, I was lucky enough to personally do the facility assessment walk down at NASA Stennis about 15 years ago. Can we go to the next slide, please? So in addition to working on space-related facilities, one of our major business lines is in mining. And mining is always a tough environmental challenge. And here's a couple images to show you just how extreme the environments are. So on the left is a copper mine called Escondida in Chile, South America. It's at an elevation of over 3,000 meters. And I think Dr. Zacny may relate to some of this as he's tested some of his gear in this desert. This is a very high desert. It requires actually medical clearance to visit this job site because of the extreme altitude. So a challenging environment. And you can see the magnitude of the mining operation that goes on. Actually, if you Google biggest holes dug on the planet, this one will come up in the top 10. On the right is another extreme environment mining operation. So the left is actually ore extraction. On the right is a processing facility. This is a facility in Fjarðal, which is a place in Iceland where we built an aluminum smelter. And the orange buildings is where aluminum is produced from alumina. These buildings are 1 kilometer long. And you're probably asking yourself, gee, I didn't know that Iceland had big aluminum deposits. Well, actually it doesn't. So in the ore processing world, aluminum is often referred to as solid electricity. It's a very intense electrical production process. And what Fjarðal in Iceland has is a brand new hydroelectric dam that produces huge amounts of excess electricity to the point where it's actually economical to import alumina to this facility and smelt it into aluminum and export it. An interesting parallel with the moon here, where there's a substantial amount of aluminum available for extraction. So let's go from mining to another industry process. If you could go to the next slide, please. This is compressing and liquefying gases. These two facilities are what we call LNG, liquefied natural gas. So again, it's a temperature and pressure controlled process on a major scale to facilitate delivering fuel for consumption in other places. Doesn't it sound like extracting water for electrolysis on the moon? But to give you an idea of scale, the image on the right is a facility called Wheatstone in Western Australia. which if you're not familiar with the west coast of Australia, it's very small population out there. Other than Perth, as you go up the continent, it's quite barren. And you can get an idea of the size of this facility by looking at the green ocean-going vessel that's in the lower right of that image. So that's a large LNG delivery vessel. And to support this, the facility is huge. It has a small cadre of operators. Again, it's small human intervention for a very large industrial process. Not only is it big and remote, the remoteness is what drives a lot of the technology to produce a facility like this. For example, a truck driver in this part of the world probably makes $250,000 a year because there just aren't any. So autonomous trucks and anything like that to reduce the amount of labor is a part of the technology here. On the right, we go to the other side of the world. This is Mozambique LNG. East Africa, so we go from Western Australia to East Africa. This is a project that's still in the development stage. Bechtel bid on this job, but we weren't successful, but there's some unique features here. This is one of the more remote places I've ever worked on a job. There are no improved roads within 500 miles of this site. One of the first things we're going to build is an airstrip, as well as dock facilities. Challenging environmentally because earthquakes will potentially liquefy the soil, and because of the low elevation, the site is subject to tsunamis as well. Again, a huge development. You're looking at, again, for scale, large ocean-going vessels to deliver the liquefied natural gas. Again, temperature and pressure control processes. Let's go to the next slide, please. So what are we looking at from a Bechtel point of view? And how will Break the Ice Lunar Challenge talk to our processes on Earth and vice versa? So we're definitely an engineering and construction services firm. We'd like to be that first general contractor on the moon that gets the big general contract to develop an open pit mine and process thousands of tons of water. That would be perfect for our goals. We also do a lot of master planning. So let me give you an idea of what master planning is. It's a vision of how a facility will develop over time. So on the right side is a vision of Libreville in Gabon, of how the Corniche and the waterfront in Libreville will develop over the next 50 to 100 years. This actually is a part of, and if you look at the image in the center top, a master plan for the entire country of Gabon. So Bechtel does everything from master planning, say, a major international airport, up to master planning at the national level. We think we could help with master planning, development of the moon or Mars. Project management is another one of our fortes of how do you pull all the contractors and material suppliers and equipment suppliers and labor brokers together. It's a huge effort for the types of projects that I've shown you. And then construction management is doing the same thing on the site. So on the bottom, we go from Gabon on the top and the right to Upper Manitoba. This is a dam project called Kiosk in Upper Manitoba, where typically you work 4 months out of the year during the so-called summer. To stay on schedule on this project, Bechtel is working 12 months around the clock through the winter in Upper Manitoba. And there are times when the temperature at this job site are colder than the temperatures seen on the surface of Mars. So we're interested in construction. We're interested in extreme environmental conditions and how what we learned from Break the Ice Lunar Challenge will translate into our work on Earth. Thank you.
Thanks, Pete. Go to the next slide, Adam. Our second panelist is Dr. Chris Zachney. Chris is the VP of Exploration Systems and Senior Research Scientist at Honeybee Robotics. His interests include space mining, in situ resource utilization, extraterrestrial drilling and sampling, and planetary geotechnical engineering. He managed numerous mining projects and production divisions in South Africa on underground gold, diamond, and coal mines. Chris?
Yeah, thank you. Thanks very much, and I appreciate being invitation. It's this topic is very close to my heart. I've been working. I came out from mining. I used to work in South African deep mines, all the way down to the 12,000 feet gold mines outside Johannesburg, and slowly, decided that space mining is my passion. So I moved from traditional mining and getting my hands dirty and so on, all the way to developing technology for space mining. It's just absolutely has been a fantastic career so far, and I hope that each one of you that's joining this challenge is gonna see as inspired as I have been, working in a mining industry, but looking up to the stars and dreaming about space mining. Next slide, please. Quick overview of Honeybee Robotics. It's Honeybee is around 300 person business, but we are owned by family-owned Ensign Bickford company that's almost 200 years old. They've been around for 200 years, and in fact, they started as a mining company. They develop explosives for mining, for tunneling, and so on. We have two divisions. Their headquarters is in Denver, and I'm running so-called Exploration Systems Group in Los Angeles. We are literally a mile away from NASA Jet Propulsion Lab that touched down just few days ago on the surface of Mars, and we were part of this mission. Just unbelievable mission. The work we do here in Los Angeles is what I refer to as space mining robots. We're developing technologies that do the mining in space, do the drilling, sample handling for two different things. The first one is touch life and to look for life in a solar system. Another one is mine the sky for in situ resource utilization. And what makes things easy for us, at least, is because of the size of the company and our sister companies, we are vertically integrated. So mechanical systems, avionics, software, release mechanisms, mission operations can be done literally almost under the same roof. Pictures at the bottom show some of the technologies that either we have developed already for missions or in a process of developing for those missions. And some of the technologies under the map of US, this is sort of ongoing development for different ISRU applications around the solar system, from Mars to comets to the moon. Europa, this is nuclear powered probe that is going to cut through 15 kilometers of Europa ice and get down to the ocean. And on the far right is a picture of myself and a colleague in Antarctica doing drilling and mining. Next slide, please. Just quick snapshot of the technologies that we have so far developed and busy developing specifically for ISRU and for mining. In 2003, we sent a rock abrasion tool as part of the 2 Mars exploration rovers. This was the very first tool that actually cut into extremely hard rocks on the surface of Mars. It was an exceptional tool that helped to uncover the history of water on Mars. A few years later, we built a drilling system with a scoop that went to the North Pole of Mars and cut into Martian ice and Martian permafrost. This is the first time we cut into Martian ice. Decades before that, we thought there is ice, And then fast forward, we actually touched ice, and this ice is pretty salty. We have a couple of payloads on Curiosity rover, dust mitigation or dust removal tool for uncovering dusting of surfaces, and the sample manipulation system that moves the sample inside the belly of the rover to different instruments. And currently, we are developing technologies for ice mining drill for a mission called Prime 1 that will launch in November or December of 2022 to the South Pole. And you can actually see the drill on the right-hand side of a lander. It's right next to it, just below, is a mass spectrometer that's going to sniff volatiles that are coming out from a drilling operation. And this will tell us the fraction and of volatiles and what volatiles are present from surface all the way down to 1 meter depth. And a year later, we are sending a Viper rover, and you've seen a part of a video that shows Viper, and the same drill is flying on Viper with a similar payload. In addition to mass spectrometer, there is a near infrared spectrometer and a neutron spectrometer. And all of those will be categorizing and quantifying resources from surface all the way down to 1 meter depth. So very, very exciting missions upcoming to the moon. And we absolutely thrilled to be part of this. Next slide, please. Now, this is about, this challenge is about mining water and other volatiles. And one of the things that we've been working on is how to actually capture water on the moon. And we developed something called Planetary Volatiles Extractor. It's essentially a large coring system that plunges into the subsurface, as pictured on the left-hand side. Once below the surface, we capture a core. We turn on the heaters on the inside of the coring system, and we heat up regolith and water inside it, sublime water away, and the other volatiles, and these volatiles go through the swivel into the cold trap. So right in the center, you see the picture of ice inside the cold trap, and just underneath you have actual water that we captured from a lunar soil simulant, with a frozen lunar soil simulant with 2 to 5 weight% water inside the vacuum chamber. And just to let you know that the biggest challenge in all of this is not really heating. It's actually capturing these water molecules. You have to have a well-sealed system. Otherwise, molecules will just fly away and escape into space forever. And making a system hermetically sealed in the presence of dust is a big challenge. So if you don't seal it properly, you're going to be losing a lot of volatiles. And once the temperature is above 110 Kelvin, sublimation essentially goes through exponential curve. So we put together this sort of concept of a water mining system. We assumed PVAX 20 centimeter diameter, 1 meter long. We assume that 75% of water is going to be lost through different leak paths. We assume 50% duty cycle, so you're mining only 50% of the time, 50% of the time you're driving around and recharging batteries and other things. And we also conservatively assume 2-8% water. So one of these things can do 1 ton of water per year. 6 of these things, like on a picture, can do 6 tons. And if you have 10 mining rovers, which is a very good thing to do because you have redundancy, you can mine 60 tons of water per year and put the water, put this water in a tank at the back. Next slide, please. And bringing back to terrestrial applications. In 2019, I was at the summit of Greenland. That's right in the center of Greenland, deploying our ice mining drills. And there is always somewhere between 10 and 30 people at the station throughout the year, including wintering over. And to get water, to get water, you have this bulldozer that's driving around, picking up snow, dumping the snow in a melter. Then the snow melts, goes through the cleaning system, and and then you can obviously use it. And then if you're in Antarctica, and that's a picture I took when in dry valleys, if you go a few inches below the surface, you have this ice cemented ground. So it's not just pure ice. You have it's not pure ice, it's ice as part of a soil matrix. So this is what we would essentially see on the surface of a moon and below the moon. And we brought our water with us, but we ran out of water. Fortunately, there was a bit of a glacier, so we would climb up and chip at ice and melt it for drinking and so on. But imagine that there is no glacier. You'll have to, somehow figure out how to actually, get water from an ice cemented ground, and that's in Antarctica. So the work you're doing right now, or you will be doing right now as part of the challenge, is directly applicable to terrestrial applications. When we go to dry valleys again, and you develop a gizmo to get water out of this ice-emitted ground, it's going to save a lot of headache for explorers and scientists that are going to these extreme regions. So with this, I'm happy to answer some questions.
Thanks, Chris. Next slide. Go to the next slide. Our last panelist is Mr. Judson Kaufman. Judson is the co-CEO of TerraDepth. He had a diverse career. He's a retired Navy SEAL, surface warfare qualified intelligence analyst, a search and rescue swimmer. After his military career, he shifted into business and founded 2 companies. He serves on the boards of multiple organizations. Judson?
Thanks, Naveen. Hey, everybody. Obviously, not an engineer, not a scientist, but been involved in TerraDepth for a few years now, and excited to share how we are solving some of the same challenges that those of you who are participating in this challenge may be faced with. So I want to provide an overview of what we're up to at TerraDepth. I think there are definitely some direct applications for you, and also probably some indirect, more analogous applications, and maybe some inspiration for new ways to do what you're out to do. So TerraDepth is a deep ocean data as a service company. So our ultimate vision is to build a virtual ocean. The virtual ocean will be comprehensive. It will be immersive. So something you could put a VR headset on and swim and dive through the ocean. Most importantly, it will be an accurate virtual ocean. So down to sub-meter resolution. And we're talking full ocean depth, which is 6,000 meters. And so at that depth in the ocean, you have extreme temperatures. It's an extreme environment. There's no light. There's a lot of unknowns in that domain. And for those of you who aren't familiar with humanity's lack of ignorance with respect to Earth's ocean, it is much more than you might expect. We understand maybe 10% of the ocean to a degree that's meaningful for decision makers. So there's a lot of ocean exploration that is yet to occur, and indeed most of it is yet to occur. So with that, I'll kick it off. Next slide, please. So you've got our vision. It's to create a virtual ocean. What our mission, so what we're really focused on a daily basis, is scaling deep ocean data collection and then transforming the way that data is shared. So it's our view that a more holistic reasoning of Earth's ocean will inform better decision making when it comes to our climate and just sort of broader Earth decisions. And we also believe that the data should be democratized and accessible to everyone. Right now, even the very limited data that's been collected of the deep ocean at high resolution, it's only available to a few militaries across the world and only a handful of large corporations. And we want to try to change that. The data that we're collecting is much more than just a map. This is a multidimensional data set. So we're talking about geological and geotechnical data, as well as the bathymetry, which is the seafloor topography, chemical data, biological data, magnetic data, also imagery and video. So we also are incorporating, water sampling devices to collect that type of physical data, much like a previous presenter discussed in collecting water samples. Next slide, please. Our view is that a complex environment like that of the surface of the moon or the subsurface of the moon, or of course the deep ocean, calls for as simple of a solution as possible. At Terradepth, we're a full stack company. So even though we are in the business of selling analyzed data, we have to build our own hardware to collect that data, because there is not hardware that exists today that allows for scale deep ocean data collection. The technology exists, but it's far too expensive. So we started with a blank canvas here on the hardware design, on the data architecture design, on the machine learning side of things, and the entire software suite, all from a clean slate, but tried not to reinvent the wheel. Mostly it's an integration challenge. So this is an overview of kind of the concept of operations, which in the world of subsea exploration and data collection, this is a novel concept. What you see here depicted are two submersibles, two data collection systems, A and B. These are twin systems, they're identical. So we only wanted to build one thing, one piece of hardware. That piece of hardware needed to be able to conduct operations on the surface of the ocean, but also conduct operations at full ocean depth. So the way that we put this together is one asset that is on the surface. It maintains constant geolocation with a satellite fix. So it knows exactly where it is. And then it sends an acoustic message to its twin that is submerged and collecting data, so that twin understands exactly how to geotag that data that it's collecting. When the submerged vehicle runs low on its lithium-ion battery power, it comes to the surface and it raises up a snorkel that can breathe air, and that air breathing capability allows it to turn on a generator, and that generator recharges the batteries. It also establishes a link with the satellite, and at that point, its twin that was previously on the surface goes subsurface and resumes data collection mission. That concept, sort of the leapfrogging through the water column, that allows us to take what's traditionally been a 48-hour autonomous mission to a 30-day autonomous mission. So it's really kind of turned the industry on its head. We're still in development phase. We haven't launched it quite yet, but most of the work is done and being tested on our prototype now. So at the end of the day, what we've done here is remove the requirement to have human beings deployed at sea, which in this case usually means having a giant ship full of people. We've reduced the maintenance cycle requirements. We've reduced operating complexity. We've reduced human cognitive load, human risk, et cetera. We've increased the navigational accuracy of deep ocean data collection through that acoustic link in the water column with the twin operation. And we're adding water column data collection. So it's critical to collect data throughout the water column, not just at the surface and subsurface, so that over time we can identify trends in climate change, organism migration, et cetera. Next slide. So to make this all work, we had to build a robot that was capable of retasking itself based on data that it's collecting in real time. Signal attenuates extremely in underwater environments, so there's not a path forward for us where a human being can kind of ride shotgun and help make decisions. The robot has to be able to do that so that we can achieve our ultimate vision here. So to do that, we had to build in a lot of compute on the edge. We had to build automatic data quality assurance. The robot needs to understand its health and state of charge at all times. It has to be able to prioritize data on the edge and be able to optimize its own route. So our human input will be, hey, here's this square. We need to go and survey this square. but you, robot, figure out the best way to do that, the most efficient path, and make that decision once you get down there. There could be a mountain or a hydrothermal vent or some subsea coral that we don't want to disturb, obviously. And so the robot has to be able to make those decisions. And of course, most importantly is automatic target recognition, which is what this kind of crude image that we collected here on a lake at Texas shows. So these boxes are targets that we previously labeled in our machine learning library that the robot automatically identified on its data collection mission. Next slide. This slide is meant to just kind of hit the talking point of keeping in mind the future potential requirements or necessity to interact with other systems. So we've tried to keep this in mind internally here at TerraDepth, and we would encourage all of you to kind of keep in mind what it looks like 10 years down the road. You know, at a certain point, there will be a commercial market on the moon, and if your hardware and software are able to communicate with more traditional systems and APIs, that's going to benefit you and just make it easier for everyone involved. So keep that in mind. You want to make your systems able to communicate with other sort of standard off-the-shelf systems. And this is an overview here of what we're using. Again, we don't want to reinvent the wheel, so a lot of NVIDIA stuff and some familiar applications you see here. Next slide. So a little bit more on the machine learning. So when we started TerraDepth, there was not in the world that we could find, I'm pretty sure it doesn't exist, a library of labeled raw sonar data. You know, if you look at terrestrial autonomous systems, there's a lot of imagery databases where those images have been labeled street sign, pedestrian, dog, tree. There's not one of those that's been developed for sonar. So we had to sort of start from scratch, collecting our own raw sonar data and then hand labeling that. And that takes quite a bit of time. And it's probably the longest pole in the tent for us. And I think that'll be part of the problem, part of the challenge for you guys as well. But you have to do this if you want to enable good decision making. So you can get to a point where you have semi-supervised training schemes, which helps you kind of enable a more rapid learning solution as you're teaching your machine how to identify what it sees. By putting a lot of this on the edge and putting that effort in now on the computer, we've got the ability to automate that data analytics and assessment, so that you're taking petabytes or terabytes or petabytes of data, which normally might take days to assess. You're moving that down into hours because a lot of it's happening on the edge. Next slide. So at the end of the day, here's kind of the high level of what we think is important, what we're trying to deliver. And I think a lot of this applies to you guys as well. So it's important to have a three-dimensional viewer. And this image here is pretty crude. We've got a long way to go on our visualization tools, but an important thing is for us is this works. This is the depth profile basically of a lake, but it's important to have a 3D viewer. So, building something that users can pan, tilt, zoom, fly through, swim through, dive through, and see from multiple perspectives. And we're doing that by, we're putting a lot of sensors on board this piece of hardware, and then we're enabling that piece of hardware to fuse those data sets in real time. You think about a human being, we have multiple senses, and we fuse those 5 senses to make decisions. The same is true for the robot. So we encourage you guys to put as many sensors as you can, because the more sensors you can power, if you can fuse that data, the better decisions that your robot's going to be able to make by itself when it can't communicate with a human. We're building point clouds. So the sonar devices are collecting data, 360 degrees. And a lot of historical maritime companies are converting that data into JPEG. We think it's important to keep the richness of that data set. So it's in a point cloud, which allows that pan, tilt, zoom, fly through capability. The track lines of where the robot actually was when the data was collected is critical. Obviously the targets and things that are not necessarily targets, but are anomalies. So we're also training our system on anomalies. So anything that we don't know what it is, but it's not just sand, it's something else. So it'll capture that image, label it as, hey, this is an anomaly. We can go back later and add that to our library as we get smarter. And of course, the geospatial mapping and the machine learning inference capability. So all this ends up being delivered as APIs for third-party integration, because there's a lot of other people that are playing in the ocean, as I mentioned earlier. Next slide. I think that covers it. Happy to take questions. I'm on LinkedIn if you guys want to find me there and follow up later. Happy to chat. Thanks.
Thanks, Jason. So Adam, we have 5 minutes left, so it's up to you whether you want to do a Q&A or go through the eligibility and registration quick.
Yeah, I'll run this through for like a minute, and then we can have a few minutes for Q&A. So as this was also covered during the first webinar and is all over the challenge website, if you want to compete, you must register online. There are eligibility requirements, more so than other challenges, including in order to be eligible for cash prizes, you must be a US-based individual or organization. International teams can compete, but they are not eligible to win cash prizes. And the eligibility information that we receive, we vet and then determine whether or not you are eligible. We have about 18, I think, eligible teams so far out of about 180 registrants. So those of you who have registered but not submitted your eligibility documentation yet, we cannot confirm that you are eligible to win cash prizes without that information. Once you are eligible, you need a team leader, and encourage you to also provide the necessary legal documentation, including proof of citizenship or permanent residence status within the United States if you want to win cash prizes. Also, please read the rules regarding information about your submissions. We've received a lot of really good questions about submissions, which is a nice progression from earlier in the challenge when we received a lot of questions about eligibility and the rules and whatnot. So we feel like we've made a lot of really good progress. We feel like the teams have as well. And I know it sounds like a long time from now, but the submission deadline is June 18th. But given the significance of some of the deliverables that are required as part of the submission, really encourage you to begin developing your solutions as soon as possible. And with that, I think we can turn to some questions.
Hey there, this is Ollie from Ensemble. So just really quickly, I'm seeing a set of questions. Some of them are related to connecting with some of the panelists, in which case, as Judson said, there's LinkedIn, and then there's also the ability to connect with them via email. But for right now, let's just look at some of the other questions. One of these kind of talks about the locations, the assumptions of the locations of the excavation site. The question is, can we assume that the locations where the excavations take place will be on an even surface, i.e. not on a slope? So it's really thinking about the environment, the kind of ground baseline environment. What are you thinking about the, and this might be—
I can take that.
Okay.
So the rules document provides the terrain and the elevation of the terrain in the excavation area. And the profile of the regolith is also provided in the rules document. Hopefully that addresses those two questions that you see. And we have tools, a video tutorial that goes, that talks about tools and techniques that you can use to understand or develop an excavation plan. Those video tutorials are on the challenge website.
Yeah, so we encourage everyone to go through those tutorials because they do define and will help answer some of these questions about the assumptions of the terrain. So we have another question that is asking about the environmental aspects of master planning on the moon. So I think this was directed more at Pete. So any commentary on, if when conducting a master plan, how environmental conditions and factors go into the consideration set for that master plan?
Certainly, I'll try and be quick on this because obviously environmental considerations are a major consideration in any master planning effort from two aspects. One is what's the existing environment? So what can you expect to challenge the vision you might have of how things will grow? So the moon, we know a little bit about the environment there, the broad brushstrokes, reduced gravity, very dusty, high radiation, micrometeor impacts, et cetera, et cetera. But I'm sure the longer you spend on the moon, the more granularity you have on what the environment is and what you need to design for. And then the other side of it is, how does your planned development affect the environment? Are you going to be kicking up more dust? Are you going to be creating piles of waste material as you extract water from existing regoliths? So there's a lot of considerations of the environment that go into a master planning effort.
Great, thank you, Pete. And so we probably have time for one more question. We have received a few other questions related to more kind of the eligibility requirements. So again, we really do recommend going through the website, downloading that document, carefully reading, because some of these questions can be answered on the website. So we have one that asks about considerations with embedding artificial intelligence machine learning systems into the kind of proposed solution. So any commentary on use of AI and machine learning and how participants should think about that in their proposed solution?
Yeah, I'll try and handle this one again. The submittals are relatively brief, 25 pages, and you're asked to concentrate on your mission architecture. How do you go from point A to point B? How do you dig material out of the ground at point B? How do you take it to point C? So the actual machine control, and I'd ask you to read the rules carefully. I believe it specifically gives you guidance on what level of machine control you need to include in your submittal. Without looking through it, I think we actually advise you to not spend too much time on the AI aspects.
Great, thank you, Pete. And with that, I think we can wrap up. Naveen, I don't know if you have any kind of final words to close us out.
Adam has the next slide, final slide.
Thank you. Thank you for those answers. I know we still have a few lingering questions. We can certainly follow up over email. And if we feel like they benefit the entirety of the challenge, then there's a likelihood that they will end up as an FAQ. As I mentioned, the deadline to submit your solutions is June 18th. Please don't wait until June 17th to begin that. We encourage you to stay connected with us, either through the challenge website or various NASA Centennial Challenges social media handles. You can also reach out to us at any time at admin@breaktheicechallenge.com. That's where we get most of our questions, and we encourage you to submit your eligibility forms and whatnot to that email address. I would also like to mention that we have begun a process of facilitating teams and collaboration. And many of you have likely received information for that. And we are continuously contacting new registrants to find out if they do want to join teams. So please be on the lookout for a new survey about possibly collaborating, because if we feel like that helps you and your prospective partners' ability to win a cash prize in this challenge, then we'd like to encourage that as much as possible. So without any further ado, I'd like to go ahead and conclude this event. Thank you so much for participating, and we look forward to following up with you all in the near future. Thanks again. Bye.